Hello everyone, this is part 8 of data communication module 4. So module 4 basically dealing with the multiplexing techniques. So far we covered the frequency division multiplexing, wavelength division multiplexing, and then we started discussion on time division multiplexing, particularly the synchronous TDM is what we are discussing. We already seen the architecture and how the system is working, everything. Now we will see some improvements that we can do here in terms of data rate management. That means if all the inputs which you are combining by the multiplexing scheme are of same data rate, we already seen all the previous examples were like that. Suppose we are combining say from four information from four different sources, and we assumed like all the four sources are having same data rate, and how we are combining them together. Now in this part we are going to discuss how we will handle sources with a different data rate. Okay, for example, out of the four, two may be of one data rate, say x bits per second, the other two may be two times of that or half of that, like that. That is the reality when dynamic or different data rate sources are coming, how we are handling it. Because for the basic multiplexing technique that we already discussed, it will be like equally we will take one unit of information from all the sources, we are combining them together in a uniform way. So if the sources are of different data rate, how we will be handling it. So one problem with the normal time division multiplexing is how to handle the disparity in the input data rate, the differences in the input data rate. In all the previous examples, problems which we discussed so far, it was assumed that the data rates of all the input lines were same, but that may not be the case in when it comes to reality. So however, if the data rates are not the same, there are certain techniques, and that is what we are going to see now. So the following three strategies or a combination of them can be adopted. The first one is a multi-level multiplexing, then multiple slot allocation and pulse stuffing. It's a very simple concept, just to understand how the things are happening here. And previously they particularly asked question from this session also, even though it is not directly given in your syllabus. So it's part of the TDM that we are discussing. So the first one is multi-level multiplexing. The name itself says that we are doing multiplexing at different levels, right? So what is happening here? Multi-level multiplexing is a technique used when the data rate of an input line is a multiple of others. Okay, for example, one of the input line is having data rate as x bits per second, another one is having a data rate of some 2x bits per second, or like that. One of the input line is having a data rate that is a perfect multiple of the other one. And what we are doing, for example, in the figure which I taken from the textbook, we have two inputs of 20 kilobits per second and three inputs of 40 kilobits per second. So like this. Okay, so here you can see that totally we have five input sources. From all the five we are trying to multiplex the information together, but see the inputs are of different data rate, right? Out of the five, the first two are having data rate that is 20 kilobits per second, the remaining three are having data rate 40 kilobits per second. Now you can see that this 40 is a multiple of 20. So that is what we mentioned here. The situation where you can apply this multi-level multiplexing is when the data rate of one of the input line is a multiple of others. Not one, just like this. It should be possible for us to combine. This 220 together makes a 40, right? So that now this 40 is somewhat equivalent to the other three. So in this way, if it is possible, you can do like this. So what we are doing is, this is the first level of multiplexing where the first two input lines are multiplexed to a single one with the combined data rate of 40 kilobits per second. So the 40 kilobits per second, now this single line is representing two actual input sources. Okay, now we have the normal multiplexing that will now be the second level of multiplexing. That is why we call it as multi-level multiplexing, and you can generalize it to more than two levels also. Okay, that you can see a situation. For example, out of this five, suppose we have six sources, and say 3 are 40, and one of the sources 20 kilobits per second, and assume that here we have two more sources and both are 10 kilobits per second. Now what we can do is this 10 together you can multiplex to 20, and this 20 you can multiplex to 40. Now this 40 you can multiplex. So now we have 3 level. Okay, and in that way you can visualize it into n number of levels. So that is the case. So once it is 40 kilobits per second, now you can use a 4 by 1 multiplexer, because now for the second level multiplexer we have 4 inputs, all are of 40 kilobits per second, and this 4 by 1 multiplexer will be combining all these 4 input lines to a single outgoing line with capacity 40 into 4, that is 160 kilobit per second. Okay, so this is one technique by which we can manage the disparity or differences in the data rate, provided it should be like this. So when you are combining them, you should be get the data rate of the other one, that this should be a multiple of this, and then only you can do that. Something like this, so the situation should be like this, favorable in this way, then only you can apply this multi-level multiplexing. The first two input lines can be multiplexed together to provide a data rate that is equal to the last three. So together in the second level we will do the final multiplexing. Hope this example is clear for you. Now in the second level of multiplexing can create an output of 160 kilobit per second. That is actually combination of the actual 5 sources, right? Now the second approach, that is a multiple slot allocation. See what is happening here. So again, from the word name itself we can see that we are trying to allocate more than one slot in the TDM frame. You know what is a TDM frame? From each input we will be taking one unit of information, which can be a bit or byte or some other unit set of bits, whatever it is, and that we will collect together and we will form a single TDM frame in the outgoing link. Now in the outgoing link, normally we will be allocating slots in a uniform way, like for every input line or source there will be a single slot. Now what we can do is, for a particular source, if you want, you can provide multiple slots, provided it is needed. Okay, so provided such a situation arise, again for handling the differences in the data rate. So sometimes it is more efficient to allot more than one slot in the frame, outgoing frame, to a single input line. That could be more effective. For example, we might have an input line that has a data rate that is a multiple of another. Just like the previous case, that multiplicity concept should be here also, but in a different way. In the following figure, we have an example where we have input lines with 50 kilobits per data second can be given to two slots. So just like this, here we have 4 input lines. One is having 50 kilobits per second data rate, 25, and if you want, you can apply multi-level multiplexing here. What you can do is these two 25 you can combine to a 50, but see, still we have the problem. So if you are combining these two into 50 kilobits per second, this is another 50 you can combine. Now what you are going to do with this 25? So such a problem is there. So here, even though this particular line is one of the input line is a multiple of other, that is maintained here, this 25 into 2 is our 50, but multi-level multiplexing, if you are doing that, may not be the good solution, because even after doing multi-level multiplexing, still we have some input line with capacity 25 kilobit per second, and we are not going to combine it with any other input line. If you have one more line with the 25, this 25 you can combine, this 25 you can combine, and totally using a 3 by 1 mux you can produce a final output. That is fine, but as it is some odd number of input line with the capacity 25, it's not possible for us to pair up them. Okay, so that is a situation. That is why we are not able to apply multi-level multiplexing. So here we have an alternative solution, again just like from the word itself it says that multiple slot allocation. So what we are doing is, in normal case, see in the as we have 4 input line, in the outgoing TDM frame there will be a slot for each one. So now if you are allocating like that, that is not a fair way, because all the 3 are having only 25 kilobits per second data rate, but this is having some 2 times of that. So what we can do is, in the outgoing frame you can allot 2 slot for the input line 1. and one slot for each of the remaining 3 input lines. So totally the outgoing frame is now will be containing, outgoing TDM frame will be containing 5 slot instead of 4 slot. Even though we have 4 input line, there will be 5 slot in the outgoing frame, and out of the 5 slot, 2 slots are for the first input line and 3 are for the remaining 3 input lines. So that is the case. So or just like we combined multiple sources of input in the previous example, that is a multi-level multiplexing. Here we are trying to do this 50 kilobits per second we are dividing into 25 each. In that way also you can visualize. Okay, so 25 now instead of this 4 input we have 5 input, all are of same data rate, that is 25. So as we have 5 input line, depending on the unit of information, whether it is a bit or byte or whatever it is, we have a frame with 5 slots, and each slot is allocated for each input line. Out of that, these 2 are actually coming from a single input source that we are dividing, just like we combined in the previous case. Here we are splitting. So you can use some kind of serial to parallel converter at this point for doing this. In the previous case we were using multiplexer at a different level in multi-level multiplexing, but here it is not multiplexing. We are actually or kind of demultiplexing. We are using some serial to parallel converter, just on 50 kilobit per second. When it is serially coming, one bit will be going here, one bit will be going like that. We will convert it into parallelly into 2 outgoing links with a 25 kilobits per second each. So that now everything is clear for it. Now the outgoing link is having a single frame is containing 125 kilobits. I mean, it's not like that. Single frame is containing 5 slot. Each slot is allocated for each input line, and together it will be providing 125 kilobit per second data rate. All together, the outgoing link capacity is this. Okay, it is not about the width of a particular frame. The particular frame width is actually 5 slot, and that depends on how many bits are there in a particular slot. It may be 1 bit bit level interleaving, it can be byte level interleaving. Like that you can decide the frame size. But all together the outgoing link is having a capacity of 125 kilobit per second, because it is combining 5 input lines with 25 kilobits per second each. Actually one of the input line is 50, that we split it like this. Okay, so this is the idea of multiple slot allocation. So we insert a serial to parallel converter in the input line to make 2 inputs out of 1, and that is for this process we are using a serial to parallel converter. So that about the multiple slot allocation, the second strategy. Now there is a third method which can be applied when the other 2 are not feasible, like whether it is multi-level multiplexing or multiple slot allocation. We have a requirement that the input one of the input slot should be a multiple of other, then only we can allocate accordingly. In the previous example it was like 25 50, so 50 we handled with the 2 slots because others are of capacity 25 kilobits per second. Also in the multi-level example we saw like it was 20 and that we combined to 40 like that. So that multiple on of the link capacity should be multiple of other, that is to be maintained to apply the previous 2 technique. But here it is applicable for other situations also. That means in general we can't guarantee that all the sources are generating data in such a way that one source is generating data which is multiple of other source. That is not possible for us to maintain in a realistic way. So this is a more practical approach which can handle other situations also, or it is particularly used when the previous 2 methods fails. Sometimes the bit rate of the source are not multiple of integers of each other. So therefore neither of the previous 2 techniques can be applied. So one solution is to make the highest input rate the dominant data rate and then add dummy bits to the input line with lower data. So this is our solution. In pulse stuffing what is happening is when we have a different input line with different input data rate, what we will do is if one is a multiple of other, we can try the previously discussed 2 methods. But imagine a situation where such multiple one is data rate is multiple of other, that concept is not there. So what we will do is we will simply check the data rate of all the input line, and out of them which is having the maximum input data rate, make it as a dominant one. So we will make other input line also we will make their data rate equal to the dominant one. So what is dominant one? The one with the highest data rate. Okay, so to make the lower data rate equal to means to increase the data rate of the sources with lower data rate to the towards the dominant one, what we can do, we can add some extra dummy and bits which are not useful, which is not part of the actual information. So we will see with an example that this technique is called pulse stuffing or bits padding or bit stuffing simply. The idea is shown in the following figures. Here we have 3 input line. The first 2 are 50 kilobits or 50 kilobits, but the third one is just 46 kilobits per second only. See, this is actually a different data rate from the other two, but it is not a multiple, or these things are there is no multiple relation between these input lines. So we can't apply the previously discussed two techniques. So what we are doing is using pulse stuffing technique. We will add some extra 4 bits in every second, so that 4 kilobits. Okay, so that this 46 kilobits per second become 50 kilobit per second. Okay, so some dummy extra bits can be added like this. Now see, we have a 3 input line or out of 50 kilobit per second. So our 3/1 multiplexer is enough to produce some 150 kilobit per second. But some wastage is there here. This dummy bits is actually an overhead because they are not part of the original information which we are trying to communicate. But still, this can solve the different data rate related issue when it comes to situation like this. That means it is if it is a multiple kind of thing, we can apply the previous two. In other situation, you can do like this. So that is the third strategy we have. So input input with the data rate of 46 is pulse stuffed to increase its data rate to 56 kilobit per second by using dummy bits. Because this 50 is the dominant data rate here. So now the traditional multiplexing can be applied at the next level. So that about the 3 techniques for handling disparity or differences in the input data rate: the multi-level multiplexing scheme, multiple slot allocation, and the third one, the more general approach, that is a pulse stuffing approach. But still here we have some wastage of information, overhead of information, but okay. So like that we have 3 techniques. Just in a theoretical way, you should be able to write if they are asking a question like that. Now to make the concept more clear in a problematic way, I taken on example problem also from this area. See that. It was like this, the question I taken from, as usual, 4000 textbook, and in that question the author is trying to ask like this: we have 2 channels, one with a bit rate of 100 kilobit per second and another with a bit rate of 200 kilobit per second. So definitely the input data rates are not equal, so we have to apply some kind of data rate management technique which are to be multiplexed. And how this can be achieved? So we already discussed 3 techniques. Then can you tell me which technique is more suitable here? If you are applying the last one, that is a pulse stuffing, see, in every second you have to stuff 100 kilobit per second kilobits additionally, and that is just a wastage of technique, and so that is not needed, because here you can observe that one of the input line is having a data rate that is a multiple of the other one. So the first discussed 2 technique, only one of them you can apply. And again, multi-level is not feasible here, because 100 with which you are going to multiplex to produce this 200. Just we have a 100 kilobit per second channel and 200. So the most apt multiplexing data rate management technique is here is of course a multiple slot allocation. So what you can do is, for this input line you can allocate, if you are allocating 1 slot for this input line, you can allocate 2 slot, because it is just data rate twice of this, right? If it is some 300 kilobit per second, then you can allocate 1 slot for this and 3 slots for this, so like that. And finally, you are trying to equalize the data rate of all the input. Okay, we are giving equal preference to all the input lines. So that is what is happening. As it is having more data rate, we have to give more attention to it. How we are giving more attention? By allocating 2 slots for this input line. Okay, so now in the outgoing link, so it can be achieved with the help of multiple slot allocation, the second data rate management technique we learned. And what is the frame rate now? Rate, the number of frames transmitted per second, and that we have to calculate. And what is the frame duration? Of course, to calculate frame duration, we need frame data rate, and you know how the duration and data rate are related, just inversely related to each other. Means bit duration will be 1 by bit rate, that's all. So similarly frame duration will be 1 by frame rate, that's all. So first you have to calculate frame rate, then you can take the inverse, that will give you the frame duration. And what is the bit rate of the outgoing links? To calculate, suppose we got x frames per second, then to convert that x frames to second to bit rate, simply multiply each the frame rate with the number of bits per frame, that's all. So all those similar questions we already seen. But now it is something that involves different data rates, that's the only difference. So what we can do is we can allocate one slot for the first channel and 2 slots for the second channel, so that the multi-slot allocation can be opted to equalize the data rate of the input lines. So now what is happening, each frame is now containing 3 slots, and each slot, the unit of information, as it is not given any hint in the question, you can either take a 1 byte per slot, or you can take a 2 bits per slot, like that. Different variations of questions we already seen, but in the question they are not mentioning anything about the unit of information, but you can assume let it be 1 bit. So be the unit of information, the very basic assumption. So what is happening here, within a frame there will be 1 bit that is coming from input line 1, and 2 bits will be taken from input line 2 within a single frame, so that the data rate is now equalized, so that each frame is now containing 3 slots, and in each slot we are storing 1 bit, so that totally 3 bits, and that 1 bit information is not in the given question, but we assumed so, as no other information is given. So now tell me, what is the frame rate? And you know, whenever the data is getting ready at the input line, the outgoing line should take the data. There should not be any delay for the input line. So that is our requirement, right? So to get that continuous flow of information in the outgoing line, what you have to do is you have to make the frame rate equal to the bit rate of the input line. But as input lines are having different bit rate, you just take the basic one, because this is 100 kilobits per second, and accordingly we are taking 1 bit from here. So whenever this 1 bit is ready, the outgoing frame should take it and move flow through the link. Okay, so 100 kilobits were getting ready per second. So what you have to do, you have to generate 100 kilo frames per second, then only each frame can take 1 bit from this, and of course 2 bits per second, 2 bits from this. Okay, so what is happening is the frame rate now has to be the same 100 kilo. So the inputs are getting ready in a rate of 100 kilo bits per second, and you have to generate your frame in such a way that there should be 100 kilo frames generated per second, so that each frame is containing 1 bit, and certainly this 100 kilobit per second is managed, and that continuous flow is maintained. Hope this is clear. Same concept I explained in the previous examples also. So the frame rate has to be 100 kilo frames per second, or 100 into 1000 frames per second. Okay, so 1 lakh frames per second, because it carries 1 bit from the first channel accordingly. Now whether it matches the speed of the second channel also, yes, because 100 frames are getting means moving, and our multiplexer is generating 100 frames in every second. Such a faster multiplexer we are having, and in with this 100 frames per second, how we are achieving 200 kilobit per second for the second input line? That is because within each frame now we are carrying 2 bits from the second data line. So 100 frames are getting generated in every second, and every frame is now containing 2 bits from the second input line. So 100 into 2 bits, totally 200 bits are we are actually taking in every second in the outgoing link. So that 200 kilobits. 200 kilobits are coming and 200 kilobits are taking. So both input and output speeds are now matched, and without any waiting, second input line can also service the information to the receiver. So as usual, I already told you how to calculate duration of the frame. That is just inverse of frame rate. Okay, that relation everything you know, because how many frames are generated per second? In 1 second we are generating 1 lakh frames. Then what is the time taken to generate a single frame? 1 by 1 lakh seconds. So that is a frame duration, or that is nothing but 10 microsecond, because denominator we have 10 raised to 5, multiply numerator and denominator by 10, we will be getting 10 divided by 10 raised to 6, and 1 by 10 raised to 6 is 10 raised to minus 6, 10 into 10 raised to minus 6 second, 10 raised to minus 6 is nothing but micro. So 10 microsecond is our frame duration. Now as usual, bit rate is, there are 1 lakh or 100 into 1000, that many frames being generated per second. Now each frame is carrying 3 bits, so the total bit rate of the outgoing link will be 1 lakh frames per second into 3 bits per second. So together we will get 3 lakh bits per second, or 300 kilobits per second as the data rate of the outgoing link, which is just a combination of this 100 and 200. So that is our requirement, right? Now the same thing, like you have to note down that because of as each frame is containing 1 bit from the first channel, the bit rate of the first channel is preserved, because first channel bit rate is 100 bits per second, and we made our frame rate also 100 frames per second, so that is being been. Now what about the bit rate of the second channel? That is also preserved, because now each frame is containing 2 bits from the second channel, so 100 frames per second into 2 bits per frame, so we are preserving the 200 kilobits per second of the that is the data rate of the second channel also. So that about the data rate management. I think with this example the concept is very clear for you, how the things are happening, and this is something that is needed in our when we try to apply this multiplexing in our practical situation. So you should have a idea about it. So with this we will wind up this session, and some more few topics and that we will cover in the next session. After that we move on to statistical TDM. Okay, thank you.